Good morning, dear students. My name is Ferhan Mazher, and today is 9th of May 2021. And right now, I am here with you. We are studying the subject of physics 5054. It's O levels physics. Today, we have set our hearts to solve October November 2018 2 paper. This paper is a theory paper, and in this session, in this video, we will be solving the section A of this paper. The section B of this paper. The section A of this paper we have already done. We have uploaded in the YouTube channel. My YouTube channel, you can watch it. And today we are working only on the section B of this paper. So let's start today's paper. And here we go. The first question is coming up on your screen. So it's October, November 2018, a 2-2 paper. This paper is from the zone 2. The question number 8 is on your screen. Section B we are doing. During a game of cricket, a player hits a ball with a bat. The ball then travels vertically upward as shown in the figure 8.1. The speed of the ball as it leaves the bat, let me reduce the size so you can see the whole thing. Okay, the speed of the ball as it leaves the bat is 8.7 meter per second. The mass of the ball is 0.16 kg. State what is meant by mass. Mass is the amount of substance or amount of matter in a body. Its unit is kg. SI unit is kg. Okay, so state the name of measuring instrument that is used to determine the mass. We use the pan balance. Pan balance is used to measure the mass. The next question is, he says, calculate the kinetic energy of the ball as it leaves the bat. The formula for the kinetic energy is 1/2 mv square. 1/2 mv square, 3-mark question. 1/2 mv square, we know the mass of the ball, it's 0.16 kg, and the speed of the ball is 8.7 meter per second. So 1/2 mv square. Apply that formula, do this calculation, you will get the answer. I've done this on a paper. Let me show you my work. So here we go. So here we have mass is the amount of matter in a body. Mass is also a measure of inertia. 2 was the pan balance used to measure mass. Question number 8, a second part. Kinetic energy is the question. Kinetic energy is equals to 1/2 mv square equals to 1/2 0.16 into 8.7 square equal to 6.05 joules. When I will round it off to the two significant figures, it will be 6.1 joules. 6.1 joules is the answer. Okay, so let's check the marking scheme. With the marking scheme, because we are done with the numerical of 3 marks. So let's see question number 8 coming up on your screen. Let me increase the size. You can see the whole thing. Okay. So quantity of matter in a body, balance of scales, 1/2 mv square, and the final answer will be 6.1 joules. It's a 3-mark numerical. I hope you have understood. Very easy and straightforward question. Okay, so let's move to the next part. Okay, so here we have okay. Figure 8.2 is the velocity time graph for the ball. Figure 8.2 shows that immediately after being hit, the ball has a negative acceleration. State the name given to a negative acceleration. Negative acceleration is called deceleration. The negative acceleration is called deceleration, or we also call it retardation. Retardation. The negative acceleration is called deceleration, or we call it retardation. 1-mark question. And before going further, let's understand one thing. When a ball is thrown upward, whenever a ball is thrown upward, remember that when you throw a ball upward, it goes upward. When it's launched, its velocity is maximum. When it is launched, its velocity is maximum. And as it goes up, its velocity gradually decreases. When it reaches the maximum height which it can attain, at that point, its velocity becomes 0. And then the ball starts coming downward. then the ball starts coming downward. Remember, when you launch, and if going upward, you take that velocity as positive, so it will have maximum positive velocity. Gradually, that positive velocity will be decreasing, 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 decreasing. At maximum height, the velocity will become zero, and then the ball will start coming downward. If going upward is positive, then coming downward will be negative. So when the ball is here, its velocity will be zero, and then its velocity will gradually increase. But now the ball is coming downward, so the velocity will be negative. So when the velocity is positive, it means, although the velocity is gradually decreasing, it's positive, it means it's going upwards. And when the velocity is negative, it means the ball is coming downward. And when it will touch the ground, its velocity, when it's coming down, its velocity will be negative, but it will be increasing. Negative velocity will be increasing in negative numbers. So, and when it will touch the ground, velocity will become zero. So this is the theory behind it. So if going upward, you took this positive velocity, then coming downward will be the negative velocity. So when you're going upward, you are working against the gravity. So you apply the force, you have launched, and then you do not apply force on it. So the only force acting there will be now the weight, because the driving force which you have given, you gave it, and then you are no more giving it the driving force, or the thrust, you are not giving it anymore. So with the initial thrust which you gave it, it will go up. The weight will be acting downward, so resultant force will be downward. So because the body will be going upward, it will be moving against the resultant force. So that will be, it will be slow down. It will slow down. It will slow down. Because whenever you move opposite to the resultant force, basically it's kind of breaks. The body will gradually slow down. The body will decelerate. But when it is coming downward, you are moving in the same direction. You have the resultant force, which is the weight, which is downward. So what will happen? Your speed will increase. If the resultant force and the direction of the motion is in the same direction, the body will speed up. It will accelerate when it's coming downward. So the speed of the body will gradually increase. But if you are moving opposite to the resultant force, the body will slow down. So that's why when the ball moves upward, its velocity gradually decreases, and when it comes downward, its velocity is increasing. But going upward, if we suppose that it's positive, then coming downward will be the negative velocity. So look at this graph. Here you have a velocity on the y-axis, and you know the velocity has direction. So here velocity is positive, and here the velocity is negative. So on the y-axis, I have velocity, which is in meter per second. And on the x-axis, we have time. So when the ball was launched upward, the initial velocity is 8.8, it's 8.8, sorry. It's 8.8 meter per second. If you look at this value, how much is this? When you launch the ball, it is every small square is 0.4. So this is 8.8. So the velocity is 8.8. So what's the velocity here? It is 0.88 or 0.89. The time here is this. So when you launched it, the initial velocity was 8.8 meter per second. And after 0.89 or 0.88 seconds, the velocity of the ball becomes zero. When the velocity of the ball becomes zero, it means it's at its highest point. When you launch it upward, when it will reach its highest point, its velocity will become zero. And then the direction of the velocity will change because it will come downward. I think you understand. I hope you understand. Okay. So the name given to negative acceleration. The negative acceleration means deceleration, or we call it retardation. State how the graph shows that the ball has a negative acceleration. If you look at here, if in a graph you are moving towards the right and the graph is coming downward, if you move in a graph from left to right and you observe that the graph is coming downward, that means that the acceleration is negative. It means that the gradient is negative. If you calculate actually the gradient of this line, that gradient will be negative. Apply the formula y2 minus y1. Take 2 points here and calculate the gradient of this line. That will be negative. So y2 minus y1 divided by x2 minus x1, that is how you calculate the gradient, and that will be negative. We know we have the negative acceleration because the gradient of this velocity time graph is negative. So that's why we are saying it's gradient, it has negative acceleration. He says using the figure 8.2, determine the time at which the ball stops moving upward. So, you know, when the velocity will become zero, the ball will be at its maximum height, so it will stop moving upward. So I have already checked with you that at what time the velocity becomes zero. At this point, you know, this time is 0.88 or 0.89, you can say, approximately seconds. At that time, the velocity became zero, which means the ball has reached its maximum height. He says the distance traveled before the ball stops moving upwards. It's a 2-mark question. The distance traveled before the ball stops moving upward, it means that the height gained by the ball when it was moving upward. So when the ball was moving upward, this is that portion. This triangle. You can see that this triangle. Just find that distance. Find the area under the graph. The area under the graph will be equal to the distance traveled. So it's a triangle. So find the area of this triangle. 1/2 base into height. The base is this. That is 0.89, and the height is 8.8. So 1/2 base into height, and you will be able to find out this is the question, the area under the graph, and that will be equal to the distance traveled. Let me show you my work. I have done this on a paper, and then we'll see. I've done this. Okay. So here we have the whole question. You can see that he says that negative acceleration is called the deceleration. Gradient of the graph is negative, and the time equals to 8.9 seconds. And the distance will be equal to 1/2 base into height, 1/2 into 8.9 into 8.8, and 38.72. And that is the distance traveled. 38.72 meter. That's 38.7 meter. That's the distance traveled. So I hope you have understood that how we find the distance traveled by the peak time graph, area under the peak time graph. So let's check the marking scheme, what the marking scheme has to say. So here we have the marking scheme. You can see it says that deceleration will turn a negative gradient or the lines of downward left to right, or 0.88 seconds to 0.90 seconds. That's the range of the answer. Our answer is in this range. And area of the counting squares, 1/2 base into height in some form, and the answer will be from 3.7 to 4.1 meter. 3.7 to 4.1 meter. So let me check what our answer is. The answer which we gave, that is, oh, there is a problem. I said 38.72. So there is a problem with the decimals. Yeah, I got the problem. So here we have, by mistake, let me correct it. So let me correct it. Because I wrote. So let me show you how I make the correction. This number is wrong. And this number. This is not supposed to be 8.9. This is 0.89. This number here is 0.89. So let me correct it. Okay, this number is. Okay, this number is 0. This number is 0. This number is 0.89. Okay, this number is not. Okay, so let me put a bracket here. By mistake, I wrote So 1/2 into 0.89 into 8.8, and let me check my calculation because there has been some issue. Okay, so let me get the calculator. Okay, so 0.89 multiply 8.8 divided by 2, and that will be 3.91. It will be 3.91, 3.91. So it was 3.9 approximately. So here I will write this answer. Okay, this is 3.9 meter per second. So let me make it opaque. And this is the right answer. So I made a mistake here. So hopefully this is corrected now. Let me correct this one. I made a mistake here. So take it back to there. Okay. So that's why we always say it's very, very important that you check your your marking scheme. You see, even we make mistakes. Sometimes we write some decimal, means some number mistake can happen. Okay, so now we will check it again. 3.9. Our answer now is 3.9. That's why it's very important to check the marking scheme. Yeah, now it's in the range of that answer. So why I made a mistake, let me show you how I came to do that mistake. So this is 8.8. That is right number I chose. Here, this is 0.89. I wrote it 8.9. So this is the mistake. So it's a 0.89. So hopefully you understand that what mistake I have made. Okay. And never make that mistake. So just why the graph in the figure 8.2 is almost vertical when the time is 1.84 seconds. At the time 1.84 seconds, you see, the ball was coming down. That's why the velocity is negative. Negative means it's coming down. And when it's coming down, its velocity is increasing. That's why you see the velocity was 2, now -4, that's -6, -8. And at 1.84 seconds, all of the sudden the velocity became 0. At 1.84 seconds, because it touched the ground. That's why the velocity has become 0. And so that's why the graph in the figure 8.2 is almost vertical when the time is equal to 1.84 seconds. The graph became vertical because the ball has touched the ground, and there is a very large deceleration has produced. When it hit the ball, all its velocity all of a sudden becomes 0. Okay, in a very short time, its velocity becomes 0. So that's why the graph has become vertical, because the value of the deceleration is quite large. That's why the graph is vertical. Let me show you my answer. So here we go. A ball has hit the ground, amount of deceleration is very large. That's why the graph is vertical. So let's check what the marking scheme has to say. I always tell you that it's very, very important when you are doing questions to check the mark. Ball hits ground on or short time for deceleration or large force of ground is hard. So ball hits the ground. In a very short time, deceleration has been produced. The next question is, figure 8.2 shows that the ball remains stationary after a time of 1.84 seconds. Describe the energy changes that is occurring at a time of 1.84 seconds. So when it was coming down, it hit the ground. Here he has all its kinetic energy, its gravitational potential energy is converted into kinetic energy, totally converted into kinetic energy, and that will be converted. When it hits the ground, I think some sound will be produced, some heat will be produced, and internal energy of the ground and the ball will increase because their temperatures goes up when they collide with each other. Okay, so let's check what I have written, and then we will. Kinetic energy of the ball is converted into the thermal energy. Internal energy of the ball and the ground will increase because when they collide, the ball collide with the ground, the internal energy of both of them will increase and their temperature will rise. So all of that will be converted into heat. Okay, so internal thermal energy of the ball and the ground has increased internal energy from kinetic energy. Kinetic energy will be converted into internal energy. And and some thermal energy will be produced. Okay, so we are moving to the question number 8C part, and let's see what the question has got. Question number 8C part is, for this ball moving in the way shown, the effect of the air resistance is negligible. When a ball with such a smaller mass is hit vertically upward at the same speed, air resistance produces a noticeable effect on its motion. So there's two ways in which the velocity time graph for the ball with the smaller mass differs from the figure 8.2. If the air resistance is present, then these lines cannot be straight lines. One effect of the air resistance. Because then the acceleration, deceleration produced will be not uniform. It will be non-uniform. So these graphs, the velocity time graph will not be a straight line. It will be curved. When the air resistance will be present, then the ball will go to less height, and it will take less time to reach whatever will be its highest point. So this point will not be at 0.89 second. It will be at a smaller, earlier. This point will reach earlier, and the ball will reach to a lesser height. So the graph will be a curve, not a straight line. And the area under the speed time graph will be also less. So let me check, let me show you my written answer, then we will see what the marking scheme has to say. This is question number 8, part C. It will take less time for the velocity of ball to become 0. Graph will be not a straight line. It will be a curve, a little curve. Okay, so let me show you. Okay, so what the marking scheme has to say. Any two from smaller time to drop to 0 velocity or hit the ground. Line not straight or velocity does not change uniformly, or gradient is not constant. Smaller area under the first part of the graph or less distance traveled. Slower final velocity, initial downward gradient steeper. Yeah, the graph will become more steeper because the value of the deceleration will be now greater. Okay, so that was the question number 8C part. Hopefully you will be able to write these answers. When I was doing a numerical, I made a mistake, and I told you that mistake. When I was calculating the area under the graph, I made that mistake. I noted the time as 0. The original time is 0.89 seconds, but I noted it as 8.9 seconds. So that was the mistake. We have corrected it, and we are good to go. Okay, now let's move to the next one. Let me save this. Okay, now we are moving to the next part. That's the question number 9 coming up on your screen. Okay, the first question coming up, just both sound and ultrasound are waves that travel in the solid, liquids, and gaseous state. How sound differs from the ultrasound? You see the sound which we can hear, its the frequency is from 20 to 20,000 hertz, but the ultrasound frequency is more than 20,000 hertz. So the main difference is in their frequency. So the sound frequency can be any frequency, but the ultrasound frequency is more than 20,000 hertz. Let's check what I wrote, and then we will see what's the marking scheme. Okay. Sound frequencies from 20 hertz till 20,000 hertz. We are talking about that sound which we can hear, whereas the frequency of the ultrasound is more than 20,000 hertz. Okay, so let's check what the marking scheme has to say, because the wording which I used. Frequency of the sound wave is smaller, or its frequency is less than 20,000 hertz. So that was the question number 9, A part. And let's do the B, next question. B, sound and ultrasound are longitudinal waves that consist of compressions and rarefactions. Explain what is meant by a wave and describe how a longitudinal waves differ from a transverse wave. You see, wave is basically the transfer of energy in a medium from one point to another point without net movement of the particles of the medium. Wave is a transfer of energy in a medium from point A to point B without net movement of the particles of the medium. This is called the wave motion. And the longitudinal wave and the transverse wave, how a longitudinal wave differs from a transverse wave. In the longitudinal wave, the particles of the medium, they vibrate parallel to the direction of the wave. In the longitudinal wave or compressional wave, the particles of the medium, they vibrate parallel to the direction of the wave. And in the transverse wave, the particles of the medium vibrate perpendicular to the direction of the wave. In the longitudinal waves, it consists of compressions and rarefactions, whereas the transverse waves, they comprise of troughs and crust. So these are the two major differences. You can, a very famous 3-mark question, very, very famous question. So let's check what I have written as an answer, and then we will move on. This is question number 9B part. The transfer of energy through a medium without net movement of the medium is called wave. In longitudinal waves, particles of medium vibrate parallel to the direction of the wave. It consists of compressions and rarefactions. Transverse waves, particles of medium vibrate perpendicular to the direction of the wave. Transverse waves consist of crust and troughs. So I hope you will be able to write good answer on it. Let's check the marking scheme. What the marking scheme has to say. Transmission of energy through a medium with no net movement of medium or vibrating particles, vibrations parallel and anti-parallel to wave energy travel direction cannot be polarized. That's the 1-mark, 1, 2, 3, 3-mark question. Hopefully you have understood. Okay, so let's move to the next part. The next part in the question is, figure 9.1 represents a longitudinal wave of frequency 25,000 Hertz traveling in oil. On the figure 9.1, mark 2 points at the center of 2 different refractions and label each one R. Okay, so this is the center of the refraction. Here I will write R. This is the center of refraction. I will write R. This is the center of refraction. I can write R. On the figure 9.1, draw a double-headed arrow to indicate a distance that is equal to 1 wavelength. So the distance between the one center of refraction to the next center of refraction, that will be equal to the 1 wavelength, 1 lambda. Then he says, measure the length of the arrows drawn on figure 9.1 and use it to determine the speed of the wave in the oil. So I know the frequency of this ultrasound, that's 25,000 Hertz. If I know the frequency and I know the wavelength, I can find out very easily the speed. V is equals to F lambda. I will use that. Let me show you my work. I've done this and then we can continue. Okay. So here we have, you can see here I have marked, here you can see I marked the center of refraction. This is the center of refraction. This is the center of refraction. The distance between this refraction, the adjacent refraction, that is 1 wavelength. We say lambda. So that is lambda. You can also do it here. Okay. So with the help of scale, if you have the hard copy, please put a scale on this and measure this. And you will get it in centimeters and then divide it with 100. It will be converted into meters. And then I will use it. So with the help of the scale, measure how much is this length. And that will be in centimeters. Then divide it with 100 and it will be converted into meters. I will use that way. So let's move to the next part. So V is equals to F lambda. So it will be 25,000. I have measured it and that is approximately 0.047 meter. So 25,000, this 0.047 meter came from actually measuring that red line, that wavelength. And then I converted it to meters. So the answer will be 1175.0 meter per second. If you write it in the 2 significant figures, it will be 1200 meter per second. It will be 1200 meter per second. So hopefully you have understood. So let's check what the marking scheme has to say. The marking scheme says 1200 meter per second, 0.047 meter will be the wavelength. When you will measure it, it will be in the centimeters. And then divided with 100, it will be converted into, meters. So let's go to the next part. He says, next question comes up on the screen. A sound traveling in a liquid passes into air. State what happens to the speed of the sound wave as it enters the air. The speed of the sound in the liquid will be more. The speed of the sound in the liquid will be more. And when the sound will enter into the air, speed will decrease. The speed will decrease. That's the characteristic of the sound. When it enters from liquid into air, the sound travels faster in the liquid and it is slower in the air. So speed will decrease. He says the wavelength, the wave in the liquid travels toward the surface at an angle. Figure 9.2 shows the center of the compression of the sound waves in the liquid. Some compressions shown have reached the liquid air boundary. The part of these compressions in the air are not shown in the figure 9.2. What they want. On the figure 9.2, draw the parts of these compressions that are in the air. So we have to draw the when these will reach. So when they will reach here, when these will reach in the air, so we have to draw the refracted wavefronts of the sound wave. This is not a water wave, remember. It's a sound wave. And when it comes into the air, its speed decreases, so it will bend towards normal. Because the speed of the sound decreases when it comes from liquid into air, the speed decreases. So what will happen? It will bend towards the normal because the speed will decrease. So it's a 3-mark question. I have done this. I have drawn it. Let me show you how I have drawn this. These wavefronts, a very important question. Okay, so here. The speed of the sound will decrease. That is the first part. Question number 9C, first part. And now we will learn how to do that sound wavefronts when they go from liquid into air. So here you can see that is the original diagram. You can see that here the wavefronts are shown. These are the centers of the compressions, and they are basically the wavefronts. This is the direction line. This shows the direction of the wave, and this is the boundary between the air and the liquid. So this is the point of incidence. So I will put a protector here, and I will mark a normal. I will mark a normal at this boundary at this point. So let me show you. So here you can see that I have placed a protector here at the point of incidence, and I will mark the 90 degree. So to mark the normal, actually I put a dot here and then I will join these points, and that will be the normal. So that will be the normal. So let me show you here. You can see with the dotted line, I have drawn the normal. So when the wave fronts will enter into the air, the speed of the air, the sound will decrease. So the wave fronts will bend towards the normal. So the direction line will bend towards the normal. Here you don't have to do the calculation. How much will be the angle? You don't have to go into the calculation. You only simply a thumb rule that it will bend towards the normal. You don't have to do the calculate that how much angle it will bend. It will only bend towards normal. That's the simple rule. Okay, so here you can see I have drawn the direction line in the air. This is the direction for the sound waves. They have bended towards the normal. And now I will draw here the refracted wavefronts of the sound wave. Now you can see this is how we will do it. I will put a protector in such a way that its crosshair and its 90-degree mark, they both are on the direction line. You can see this 90-degree mark and this crosshair, they both are on this direction line. So I will move it little downward when it will touch this point where this wavefront is touching the boundary. It touch this it touch this straight edge of the protector. So I will take a pencil and I will draw along this straight edge. That will be the refracted wavefront. So let me show you. Here you can see that with the red color I have shown that wavefront. Then I will again put my protector. The precaution is that the crosshair and this 90-degree mark, they should be on that direction line in the air. I will move the protector a little downward when it touches this point where the wavefront in the liquid is touching the boundary. So along this straight edge, I will draw this line with the red color. I will draw this, and that will be the refracted wavefront of the sound wave. So here you can see that second refracted wavefront I have drawn. Okay, so now I will again put the protector, and you can see the crosshair and the 90-degree mark, they both are on the direction line. I will move this protector a little downward. So when it touches this point where this third wavefront is touching with the boundary, and this straight edge of the protector is also coinciding with that point, I will draw a line along the straight edge. That will be the refracted wavefront. I will continue doing this process. Here I have only shown you 3 wavefronts. You can draw the 4th one also. So I hope that you will be able to understand that the sound waves, when they enter from liquid into air, the one thing which you should understand is their speed will decrease. The speed of the sound will decrease. So that's why the wavefronts will bend towards the normal. And this is how you draw the wavefronts of the sound. Remember one thing, the behavior of the light will be different. When the light will enter from the liquid into air, the speed of the light will increase, opposite to the sound. When the light will enter from liquid into air, its speed will increase. That's why when the light will enter from liquid into air, it always bends away from normal. But the sound has a different behavior. The reason is when the sound enters from liquid into air, its speed decreases. So it will bend towards the normal. And in the case of light, when it enters from liquid into air, its speed increases. So it will bend away from the norm. Hopefully you have understood. So let's check the marking scheme, what the marking scheme has to say. Let's check. He says 4 or 5 straight lines in air that touches the compression still in the liquid and no intermediate extra lines between the correct lines. At least 4 compressions in the air. I have only drawn 4. You can draw I have only drawn 3. You can draw 4. He's asking for 4. Okay, so 4 compressions in air parallel to each other. At least 4 straight lines in shallower angle with the horizontal and slope correct. So we are done with that thing. Okay, so we move to next question. The next question coming up on your screen is, so this is the question. Describe in outline how ultrasound is used in cleaning. You see what we do, we take a utensil, in that utensil we put some cleaning fluid, and then for example, let's say for example, you have jewelry and you want to clean that jewelry. So what you will do, you will submerge or dip the jewelry into that cleaning liquid, and then we have ultrasound emitter. So we will emit the ultrasound pulses into that cleaning fluid. Due to the vibrations of the very high frequency vibrations of the ultrasound, what will happen? The dust particles which are collected on the jewelry, they will be dislodged. They will be separated from the jewelry. Separated means they will be dislodged. Actually, the word is dislodged. Okay, so the jewelry will become clean. So this is how we do this. So let's move to the next part, and let me show you my answer. I've written this answer. So here we go. Question number 9, D part. Let me increase the size. Jewelry to be cleaned is submerged in the cleaning liquid. High frequency ultrasounds are produced in cleaning liquid by an emitter. Due to the vibrations, dust particles are dislodged from jewelry. jewelry becomes clean from dust. So this is how you do this. This was question number 9. Let's check the marking scheme, what the marking scheme has to say. So here you can see that question number 9, D part. Object to be cleaned, immersed in the liquid solvent. 1 mark for this. Object liquid, agitated, vibrated, or by ultrasound. Dirt particles shaken off or dislodged to remove dirt. So this is the 3 marks question. I hope you will be able to write the answer. So we are done with the question number 9. Let's move to the next question. And the next question coming up on your screen is question number 10. So here we have the question number 10. He says, a student sets up the circuit shown in the figure 10.1 in a laboratory at room temperature. The electromotive force of the battery is 12 volt. The switch is closed. The connecting in the circuit are made from copper covered. State the name of the particles that flow in the copper and state the direction in which they are flowing at the point. So here we have that circuit. So in this circuit we expect its EMF is 12 volt, and in this we have 12 volt is the EMF, and here we have the switch. Here is the point Y on which the question is asked, and here we have a 1.5 ohm resistor. Here we have component Z. They both are parallel to each other. Here we have a fixed resistor that is 1.3 ohm, and we have connected an oscilloscope CRO against it. So whatever is the voltage drop here against the time, that will be shown on the display of the CR. So let me, because we have connected the, I made the sign of that alternating current, but because here the current is DC line. You see this CRO is connected against the 1.3 ohm resistor, and the power which you are giving here, electric power, that's a DC current. I by mistake made the sign this, which is a symbol for alternating current. This is there we don't have alternating current. We have the DC current. So its graph will be a horizontal straight line. So remember this. So the question is, what will be the direction of the current? Okay, state the name of the particles that flow in the copper and state the direction in which they are flowing at the point Y in the circuit. So the particles which are flowing here are electrons. They are negatively charged, and at Y they will be going towards the bottom of the page, or you can say at Y they will be going towards the ammeter, or you can say they are traveling from the negative terminal of the battery through the circuit towards the positive terminal of the battery. They are going from the negative terminal of the battery through the circuit towards the positive terminal of the battery. So there are many things you can write here. Let me show you my written answer. I have written this. So let me increase the size. So question number 10A part, electrons are flowing in the copper wires at point Y. Their direction of flow is towards the bottom of the page, or you can say towards the ammeter. Or you can say it's from the negative terminal of the battery towards the positive terminal of the battery. So let's check the marking scheme. What the marking scheme has to say, it says electrons towards the ammeter, or away from the negative terminal, or towards the positive terminal. Okay, so let's check what's the next question is. It says, what's the name? He says name. Let me reduce the size. See. The next question is, he says, at the room temperature, the resistance of the component Z is 6.0 ohm. State the name of the component Z. This component Z, this is the sim. This is, he's talking about this. This is, and don't forget this symbol. This is thermistor. This symbol is thermistor. This is the symbol for thermistor. Right? So their question is, what's the name of the component Z? That's thermistor. He says, calculate the resistance of the whole circuit. So the resistance of thermistor is 6 ohm. Gave you the 6 ohm. So this resistance is 6 ohm. This is 1.5 ohm, and this is 1.3 ohm. So if you want to find out, the resistance of the total circuit, very easy. You see, these two are connected with the parallel to each other. They are connected parallel to each other. So you can find out their total resistance. Their total resistance will be 1 by R4. I'm just naming it 1 by R4. Their combined resistance. That will be 1 by R4, 1 by 1.5 plus 1 by 6. Just get the R4 answer. Once you have the resistance of this combination, then this and this, they will be in series with each other. So simply add them and you get the total resistance of the whole circuit. Let me show you. I have done this on a paper. Okay. So now 1 by R4 equals to 1 by R3 plus 1 by R2. 1 by R4 equals to 1 by 1.5 plus 1 by 6. Just do this calculation. It will be 5 by 6. So cross multiply and R4 will be 1.2 ohm. 1.2 ohm. And because this R4 and that 1.3 ohm will be in series with each other, so I will add them. So the total resistance of the whole combination will be 2.5 ohm. 2.5 ohm. I hope you understand. So let's check the marking scheme, or we go to the next question. Let's go to the next part and then we will see. Then he says calculate the current measured by the ammeter. The current coming out of the battery. You have to measure that. The current coming out of the battery. So the current coming out of the battery, I can calculate very easy formula. EMF of the battery divided by the total resistance of the circuit. The current coming from the battery is equal to EMF divided by the total resistance of the circuit. Let me show you my answer. I've done this. So the EMF of the battery is 12 volt and the total resistance is 2.5 ohm. So the final answer will be 4.8 ampere. So the final answer will be 4.8 ampere. 4.8 ampere. Let's check the marking scheme to make sure that our work is correct. Because sometimes, we are humans, we make mistakes. So question number 10B, first part, thermistor, that our answer is right. And the total resistance will be 2.5 ohm. And the current coming from the battery will be 4.8 ampere. 4.8 ampere. The question is, the marking scheme is in front of you. You can see our answers are right. So let's move to the next question. So the next question coming up on your screen is, he says, the current in the ammeter is IA. The current in the 1.5 ohm resistor is IR. And the current in the component Z is IZ. Write down an equation in that relates them. So the current which is here, that will be equal to the sum of these two current in these two branches. The current which is flowing through the, or you can say, if you are talking about the electron flow, the current coming here, that's IA. Here it will split into two branches. So if the current flowing here and the current flowing here, add them, that will be equal to the current flowing to the ammeter. So let me show you my answer. So, okay, here we go. So IA equals to IR plus IZ. IA equals to IR plus IZ. Very easy question. Let's move to the next part. Okay, so there we go. This is the marking scheme. The our answers are right. Okay, so let's move to the next part. He says in the next part. Figure 10.2 shows the screen of the oscilloscope. Okay, so here we have that trace of the when the switch closed, trace with switch open because the DC current. So we will have a horizontal graph. You can see here. Before the switch is closed, the trace is a horizontal line across the middle of the screen as shown in the figure 10.2. When the switch is closed, the trace remains horizontal and moves up the screen. Component Z is heated. Component Z is heated. State and explain what is observed on the oscilloscope screen as the temperature of the Z increases. It's a 4-mark question. You see, it's an important question. It's a 4-mark question. Before you answer it, let me go to the diagram and try to explain you. So here is that question. The trace is about the voltage drop across the 1.3 ohm resistor. The trace is about the voltage drop across this 1.3 ohm resistor. But when you will increase the temperature, the resistance of this thermistor will be affected. When you increase the temperature, the resistance of this thermistor will be affected. But the voltage drop on the CRO, that is the voltage drop across that fixed resistor. You see, when you will increase the temperature, when you will heat the thermistor, the resistance of this thermistor will decrease. The resistance of this thermistor will decrease. The resistance of this combination will decrease. Because this value, other two values of the resistors, they are constant. But when you will increase the heat, you will heat it, the resistance of this thermistor will decrease. When the resistance of this thermistor will decrease, the whole combination, the resistance of the whole combination will also decrease, because the resistance of the thermistor has decreased. So the current coming from the battery will increase because the resistance of the whole combination has decreased. Now the current coming from the battery will increase. So the current, whatever the current is coming out of the battery, that whole current is flowing through this 1.3 ohm resistor. Its resistance is constant. So it's 1.3 ohm. Its resistance is constant. But the amount of current flowing through here, that has increased. V is equals to IR. V equals to IR. Resistance is still 1.3 ohm, but the amount of current now has increased. So the voltage drop will also increase. So the oscilloscope trace will move further up because the voltage drop here will increase. Across the 1.3 ohm resistor, the voltage drop will increase because the current flowing through this 1.2 ohm resistor has increased. Let me show you my written answer. Maybe you understand. When thermistor will be heated, I just wrote heat. When thermistor will be heated, its resistance will decrease. Resistance of whole circuit will also decrease due to less value of the resistance of Z. Current from the battery will increase. When current through fixed resistor of 1.3 ohm will increase, voltage drop across it will increase because V equals to IR. If R is still 1.3 ohm, but the I value has increased, so the voltage drop will also increase. So the trace on the CRO will move further up. This is the answer. So let me check the marking scheme, what the marking scheme has to say about this, and then we'll see. Resistance of the thermistor decreases 1 mark. Resistance of parallel combination decreases, or total resistance of circuit decreases 1 mark. Voltage across the 1.3 ohm resistors increases. So trace will move towards top of the screen, or the trace will move upward, further upward. So that's 1 mark. It was the 4-mark question, very important. Okay, so let's move to the next question. We are doing the question number 10. Okay, now we are here. The 12-volt battery is made from cells of electromotive force EMF 1.5 volt, which are in series. Calculate the number of 1.5 volt cells that make up the battery. Number of cells, you can easily find 12 divided by 1.5. You will get the number of cells. So, and the state the EMF of a battery made by connecting all of these cells in parallel. You know, when you connect the cells in parallel, their EMF do not add up. So whatever will be the EMF of a single cell, that will be the EMF of the whole combination when you connect them in parallel. So that will be 1.5. So let me show you my answer and then we move on. Here we go. So number of cells will be 12 volt divided by 1.5. So there will be 8 cells, and the EMF of when you connect these 8 cells in parallel to each other, the EMF, the whole combination will be still 1.5 volts. So that's it. So let's check the marking scheme and then we are almost done. So this is the answer. So answer, you can see our answers are right. So, my dear students, today we have, let me increase the size. So today we have done October, November 2018 Physics 505422 paper. In this video, in this session, we have only attempted the section B of this paper. Question number 8, question number 9, question number 10. And I hope that you have understood the questions. So if this video is helpful to you, if this video is helping you to do the past paper practice of physics, kindly don't forget to subscribe to my YouTube channel. Don't forget it, subscribe it to my YouTube channel. Also, always press the like icons. And if you have any kind of comment, don't hesitate to comment, and please recommend these videos to your friends. And now I am also making a request that please share them on your Facebook. So thank you very much, everybody. I hope that this is helpful to you. Thank you very much. Have a good day. Bye.